Okay guys, so like I said, if I had to cancel class, I told you I would record a lecture, and so that's what I'm going to do today. It probably won't be as long as a normal lecture because there won't be any questions, but I'll try to go at a pace that's conducive to not being overwhelmed. And then if you have any questions when we get back to lecture in person, I'll be sure to answer them. Okay, so what we're going to talk about today is boundary value problems via the direct method in particular. But at first, let's just introduce the concept of boundary value problems, where they're similar to initial value problems. It just has to do with where you specify the conditions. So let's go to write this down. Okay. Boundary value problems. Okay, and so the main difference is that, and we discussed this before actually, was that instead of conditions being specified at a single location of the independent variable, that is what we have for IVPs, or initial value problems. We have the conditions are specified at multiple locations. Conditions are specified at multiple locations. Okay, so think of something like a thermal reservoir, like a tank, or a long aluminum rod, which is what we'll actually just talk about in just a moment, where you have, say, the temperature held constant at the ends of the rod, or you might even have a certain type of heat flux into the rod, and we'll talk about that later as well. Okay, so and let's go ahead and introduce the abbreviation BVP for boundary value problems. Okay, and then we'll get right into discussing the direct method of solving these equations. Okay, and like I said, we're going to consider a long, slender aluminum rod to discuss this type of problem. Okay, and that's going to be our model problem, essentially for the rest of the lecture, that we'll use to talk about this method, this numerical ODE solution method. So, like I said, let's consider a long, slender aluminum rod of length capital L. Okay, and when I write down these words long and slender, that's basically it translates to the fact that the problem is approximately one-dimensional. Okay, so you say it means the problem is approximately 1D. Okay, meaning that the rod is so narrow compared to its length that it's essentially like a 1D line. Okay, and what we will have is that the temperature at x equals 0 at the left hand side of the rod is equal to 40 degrees Celsius, and the temperature at x equals L, the right hand side of the rod, is equal to 200 degrees Celsius. We'll also have that the rod is immersed in a thermal bath at T infinity equal to 20 degrees Celsius. So this is like the rod being in a room temperature room, for example. Okay, in the middle of a room, far away from anything. It's not in contact with anything specific. And then we can write the following governing equation. So the governing equation becomes the following. Is that you have K times A times the second derivative of the temperature with respect to X, or the distance along the x-axis, is equal to lowercase h times capital P times the quantity T minus T infinity. Okay, so K here is the thermal conductivity. A is the cross-sectional area. Of the rod. H is the convective heat transfer coefficient. And then P is the perimeter of the cross-section of the rod. Okay? And then T infinity is just that ambient temperature. So what we're left with here is a non-homogeneous linear equation with constant coefficients to boot. So if we wanted to, we could actually solve this fairly easily. But we're going to use it as a model problem to discuss the direct method for solving boundary value problems. What we're going to do is we're going to go ahead and rewrite it just to reduce our number of constants, and we'll rewrite it as the second derivative of t with respect to x is equal to capital H times T minus T infinity, where H is equal to lowercase hp over Ka, and we'll assign the value 0.01 per meter squared to that for later reference. And then that equation paired with the boundary conditions forms our system that we'd like to solve. Okay, so now of course the first thing that we do if we want to solve this numerically is we need to discretize the rod into n segments. So now we discretize into capital N segments of size delta x equal to L over N. Okay? And so this is the same as, the last point, xn minus x naught divided by n. Okay? And we're making this transition from h to delta x. I'll try to stick to delta x when we're talking in terms of boundary value problems, and then maybe just keep h reserved for initial value problems when we're looking at functions that are a function of time as opposed to space. Perhaps that will create a nice division between the two types of problems. So we have this we're discretizing into these n segments. We can write the value of x at every grid point as x sub I, which would just be I times delta x, since we're setting x naught equal to 0. And then we have t sub n, which is just t evaluated at xn, which is equal to L, of course. And we know that that is equal to 200 degrees Celsius. and T naught, which is T, I did it again there, T naught, which is equal to T evaluated at x naught equals 0, is equal to 40 degrees Celsius. Okay? And so our unknowns are T1, T2, and so on to Tn minus 1. Okay? And those are all of our interior points. Okay? So the next step is to come up with a discrete representation of our governing equation. Okay? And we want to apply it at every interior point. And what you'll end up with is a system of n-1 equations for n-1 unknowns. In this case, a linear system that will allow you to solve for all of those unknowns at once. So, in short, to write that down, the next step is to come up with a discrete representation of our governing equation okay, and we're going to apply it to every interior point, and then what this will lead to is a system of n-1 equations, one per interior point, for n-1 unknowns. Okay, that we will be able to solve. And so if we're going to discretize our system, natural choice for doing that would be the central difference operator. And that's because we're doing all interior points, right? And we know that the central difference operator, both for the first and second derivative, is second order accurate, so it's a bit better than, say, like a forward or backward difference. And so we will go ahead and use that to discretize our equation, okay? So let me write down what I mean by that. So we want to have some sort of discrete representation of the second derivative of the temperature, okay? Evaluated at one of the interior points xj, okay? And I'll just put soup CD here to stand for central difference. And that thing we're going to say is approximately equal to, and you've seen this formula before when we first talked about finite difference approximations. It was the only finite difference approximation that we discussed for second derivatives, and it's equal to tj plus 1 minus minus 2 times tj, 2 times tj plus tj minus 1 divided by delta x squared, okay? The whole thing, delta x squared. And that approximation is second order, so this sort of squiggly line is taking into account the fact that you're going to have order x squared error, okay? And then we set this equal to h times tj minus t infinity, okay? And that equal sign is coming from the governing ODE, okay? So if we rearrange this, then we will obtain tj minus 1 plus negative 2 minus h times delta x squared. Okay, that quantity times tj plus tj plus 1 is equal to negative h delta x squared times t infinity. Okay, and then this quantity in the parentheses, we're just going to call that alpha. We're going to rename it. Okay, so let's go ahead and actually write down several of these interior equations so you'll be able to see how it gets converted into a matrix system. Okay, so now let's write these out. So the first interior point would yield the equation T0 plus alpha T1 plus T2 is equal to minus H delta X T infinity. The second equation would be T1 plus alpha T2 plus T3 is equal to minus H delta X squared T infinity. Okay, so the first equation there is the equation for j equals 1. The second equation is j equals 2 for that specific interior point. And this continues until the final equation, which would be t n minus 2 plus alpha t n minus 1 plus t n equal to minus h delta x squared t infinity. And then of course that equation is the j equals n minus 1 equation. Okay? So what you were left with, like I noted before, is n minus 1 equations for n minus 1 unknowns. And then we'll note here too that this Tn is known, and same with the T naught. These are both known due to our boundary condition that we specified. Okay, so those are both known, and if we convert this, looking at the structure of these equations, we can convert this to matrix form. So convert to matrix form. And the way that will look is, I'll leave it on the screen for a second so we can see where these things are coming from. So the first row, what we're actually going to do is we're going to move the knowns over into the right-hand side of the equation, okay, because they're known. So they'll form part of that right-hand side of the linear system. You'll see what I mean by that in just a moment. So then the first entry of our matrix is alpha, the second entry is 1, and then it becomes 0, and that continues to the right-hand side of the matrix. Then the second row, this is going to be the second equation. You have 1, alpha, 1, and then a 0, and that continues over there. And then the third equation, you can sort of start to guess the overall structure now. And then this continues down the diagonal, all three of these. Okay? And then the last couple of rows look like, let me just go ahead and close the right-hand side of the matrix here. Note that we have zeros here, and those continue down. And then the last couple of rows, we're going to have a 1, an alpha, a 1, zeros, those continue over here. The zeros here continue down. Okay, you have zeros off of the three let's say the diagonal, and then the first and second off diagonal elements. And then you have, for your last row, you'll have a 0, 1, alpha. Okay? And then this whole thing this matrix is being multiplied by what we would call our solution vector, which contains all of our interior points, the values for the temperature at all the interior points. So the first element is T1, second is T2, and so on until the last element, which is Tn minus 1. Okay? And so now you're starting to see how this system is formed by this matrix multiply. And then the right-hand side is going to be the right-hand side of the equations that we've been looking at. So the first equation, like I said, we moved over our known value. So the first element of our right-hand side vector is h delta x squared t infinity minus t naught. Okay, the second element is just that minus h delta x squared t infinity term, and that continues all the way until the last couple of elements, the second to last of which is h delta x squared t infinity, like all the other equations that don't include a boundary point. And then for the last equation, we move over that Tn unknown, and it becomes h delta x squared t infinity minus Tn. Okay? And so what we're left with is an equation where we set this, or we call this big matrix our system matrix A. We would call this solution matrix T vector, okay? And then the right-hand side here, we usually call it B, okay? So it forms this like AX equals B system. That's that notation that you're probably familiar with from linear algebra, okay? So what we have is essentially the value of the temperature. We can obtain the temperature, or the value of the temperature at all the interior points directly, and that's where that direct method name comes from, moniker comes from. We can find this value directly by solving the following system. So let's write that down. We can solve for T, capital T, temperature, at all interior points directly by solving this system, where the solution becomes T vector is equal to A inverse times B. Okay? And then just a bit of a reminder, in Python, you're going to do this by calling the function np.linealg.solve, where the two arguments will be A and B. Okay? Like I said before, we don't want to be computing inverses of matrices. It's not. This function is more stable, and it takes advantage of advantageous structures in the matrix. So one thing that I haven't noted yet is that this matrix is in a structure called a tri-diagonal structure. Okay, and we have very efficient algorithms for solving tri-diagonal systems. Okay, so that's why we that's another reason why central difference is preferred, because it results in a tri-diagonal matrix, which we can solve very efficiently. Okay, so let's talk about before we go ahead and do let's say a demo where we solve this numerically. Let's actually talk about some different types of boundary conditions. Okay, so the types of boundary conditions that we just talked about now are what are called Dirichlet boundary conditions. So types of boundary conditions. Okay, so broadly speaking, there are three types for these boundary value problems. So three types. You have Dirichlet, which is the type that we just discussed. We have Newman, and then we have mixed, or more commonly called Robin boundary conditions. Okay, BCs. So Dirichlet is the simplest type. Okay, this is where you specify the value of the dependent variable at the boundary. So this is the simplest. Value of dependent variable is specified at the boundary. So this is just like where we looked, T at 0 is equal to 40 degrees, right? So we're actually specifying the value of the temperature at the boundary point. Okay. Now, actually, I think I included a picture of Dirichlet here. So Dirichlet is an interesting guy. He early in his career, he actually studied under George Ohm, who was of Ohm's law fame. Okay, And then he went and traveled to Paris. And when he was about 20 years old, he produced a proof for a special case of Fermat's last theorem. And there was a lot of fanfare about this, and he got to meet Fourier and Poisson while he was in France. He's actually a German mathematician, despite his French name. At least I think Dirichlet is a French name, but regardless, he while he was in Paris, he was sort of influenced by Fourier and Poisson, and he eventually he did most of his work in number theory, but he eventually worked on partial differential equations. He even produced the first rigorous proof that Fourier's series converge, and that was after Fourier himself, as well as Cauchy and Poisson, had failed to prove that. He managed to do that. And then he eventually worked on partial differential equations, and he was the first to prove the uniqueness of a solution to the boundary value problem using this type of boundary condition. And that's why this type of boundary value problem bears his name. But yeah, very, very successful mathematician. And so that's why these boundary conditions are named after Dirichlet. But again, those are the simplest type of boundary condition. There's also another boundary condition called the Neumann type. Okay, so this is where you specify the gradient of the dependent variable at the boundary. And these are also very common. This is like, imagine you want to specify the heat flux into the rod. That would involve a gradient of the temperature, as opposed to fixing the temperature value at one end or the other of the rod. Okay, so Neumann. This is not John von Neumann or Neumann, the famous American polymath, but this is actually another German. There's sort of less known about him. I have another picture. I actually have a picture of him as well. This is him, and they don't quite do portraits like they used to. But he actually, interestingly enough, his uncle-in-law or by-law was Bessel of Bessel function fame. But he actually worked mostly on E&M, on a formalism that was eventually sort of abandoned in favor of Maxwell's formalization. But he was trying to establish the mathematical structures for E&M around the same time that Maxwell and Helmholtz and Hertz and all of those guys were working on their sort of branch that became the dominant branch. So he kind of believed in the luminiferous aether and all these other things that Maxwell's, him and his acolytes eventually did away with. But despite the fact that his work in E&M didn't end up being widely used, he did at one point further develop Dirichlet's work in the boundary value problems with partial differential, or with higher order differential equations, and so that's why this type of boundary condition bears his name. Let's see here. So we'll kind of linger on these Neumann boundary conditions for a second. So imagine in the problem above, we might want to specify that one end of the rod is insulated, like I said. Okay, so specify that left hand side of the rod is insulated. Okay, so what that would mean is that there's no heat flux. So heat flux in this scenario is expressed as Q double prime. It's just a notation. There's no derivative being computed here. is equal to minus k times dt dx. Okay, and then this minus sign comes from the fact that heat moves from high to low temperature. So, you know, if you're plotting t versus distance here, and your temperature is rising to the right here, the heat is going to move in the negative x direction. Okay, so so minus sign because heat moves from high T to low T. And that's actually just a consequence of the second law of thermodynamics. Courtesy of Clausius. Okay, so what we end up with is that the boundary condition would be that dt dx evaluated at x naught would be equal to 0. Okay, so that's what a sort of your standard Neumann or Neumann boundary condition would look like. Okay, and then the last type of boundary condition that we discussed was Robin. Okay, this is Victor Robin, the French mathematician. There's really not much you can learn about him. He's just he's just a sort of a quasi-famous or a semi-famous French mathematician that lived in the second half of the 19th century. He actually died at 42, so not a particularly long life. But in any event, these boundary conditions are a mixed form of the previous two. Now, you might hear the term mixed boundary conditions, and it might not necessarily be a Robin boundary condition. It just might be talking about a problem where one boundary has a certain type of boundary condition and then the other boundary has a different type of boundary condition. You know, one could have Dirichlet, one could have Neumann, but that doesn't mean that the problem is a Robin problem. Robin is particular form where you have a linear combination, so a t plus b, where a and b are constants, b dt dx. That thing evaluated at some x naught is equal to some constant. Okay, so it truly is a mixed type of boundary condition at a specific boundary. Okay, so really in the end, the boundary conditions, they function as the final equations that close the system, right? So the BCs function as the final equations that close the system. Okay, so with Dirichlet, the values of the temperature at the boundaries, or of the dependent variable in general, at the boundaries are specified. So that leaves us with n-1 unknowns. So it takes us from that n+1 to n-1 unknowns. But with Neumann or Robin, your temperatures at the boundaries, the temperature value itself is actually unknown. Okay, so with Neumann, I'm just going to jump back and forth between the pronunciation of either Neumann or Neumann. I think Neumann must be more correct. With Neumann or Robin, the actual temperature at the boundary, T at the boundary, so that would be either, you know, T naught or Tn. Whoops. Come on. T naught or Tn is not known, or is also unknown. Okay, so we have the n-1 interior equations and unknowns, but we pick up two more from the boundary conditions. So therefore we have, n plus 1 equations, n plus 1 unknowns. But in practice, usually what we do is we fold those boundary condition equations back into the first and last interior equation to maintain, the advantageous matrix structure. Okay, so what we need to do with those extra two equations is we need to pick a suitable finite difference formula to discretize those boundary value equations. Okay, so let's think about this. So at the left boundary, so if we're looking at the Robin boundary condition, okay, that has this a t plus b times d t dx, we need to discretize that dt dx term, and we need to make sure that this equation holds at the boundary. So meaning at t0 or t at x naught. And we talked about this in one of our homeworks. You're going to have to use a finite difference scheme that is only forward looking. The simplest thing that we would choose is forward Euler. So at the left boundary, we might employ a forward difference. And I shouldn't have said forward Euler there, because we're talking specifically about a difference, a finite difference approximation. Okay, so working with that Robin boundary condition, we have at plus b times dt dx, and we're going to evaluate that at x naught equals 0, and that thing is equal to c. Okay, and so if we're going to discretize that, what we'll end up with is a times t naught, okay, t at the left boundary, plus b times this function t1 minus t naught over delta x. Okay, and then that's equal to c. So that becomes our finite difference approximation or representation or discretization of that boundary condition equation. And if we actually solve that for t naught, we get c delta x minus b t1 divided by a delta x minus b. Okay, and so what we're left with is a sort of a t naught written in terms of t1. Okay, so the value of the temperature at the left boundary written in terms of the value of the temperature at the first interior point. Okay, so and then really quickly, just as an aside, for the dt dx equals 0 BC that we discussed, where that's evaluated at x naught equals 0, this becomes even simpler, right? Because if you put in forward Euler, you just get t1 minus t naught over delta x. Let me write down a better t naught here. Oops. I'll write down a better t naught so that this is clearer. So t1 minus t naught over delta x is equal to 0. Well, that's just going to hold t naught to be equal to t1. Okay? So in practice, it doesn't have to be as generally complicated as the Robin boundary condition. But we'll proceed with this Robin boundary condition t naught over here on the right side here, simply because it'll be more helpful for you to see that in the overall system. Okay, so let's actually employ this Robin boundary condition modification to the aluminum bar problem. Okay, so employ use this modification in original aluminum bar problem. Okay, and what I mean by that is we take our d squared t dx squared equal to h t minus t infinity. So that was our governing equation, same thing as before. And we're still going to have the temperature at L at the right boundary be equal to 400 degrees Celsius. But now what we're going to do is we're going to enforce this general Robin boundary condition at the left-hand boundary. So at plus b dt dx evaluated at x not equals 0. We'll set that equal to a constant c. And we'll leave these constants undetermined for the time being, just so you can see how this goes in. And so if we discretize the equation, the interior equations is all the same as before. It's still this tj minus 1 plus alpha tj plus tj plus 1 equal to minus h delta x squared t infinity. Interior equations are unchanged. The equations that change are the boundary equations. In particular, in this case, the first boundary. In fact, the last row is also unchanged from before, because the boundary condition is the same. Okay, so let's take a closer look at the first row. Okay, so what we can do is let's sub in the expression we obtained for t naught into the equation for t1. Okay, and that equation to remind you was t naught plus alpha t1 plus t2 is equal to minus h delta x squared t infinity. Okay, so if for the Dirichlet boundary condition, all we did was we moved this t naught over here. So that was Dirichlet in blue. But for Robin, what we're going to do is we're going to take this t naught that we have on the right hand side of the screen here, and we're going to sub it in to where we see t naught. And so what we'll end up with is that c delta x minus b t1 over a delta x minus b. Okay, and then the rest of the equation, of course, is unchanged. So you get that alpha t1 plus t2 is equal to minus h delta x squared t infinity. Okay, and so we're going to wrap up these two pieces of this formula into two different constants. So we're going to call what I'm circling here in green, we're going to call that gamma. Okay, and then what I'm circling in, let's see, I might as well use red. What I'm circling in red, so the b divided by that denominator, we're going to call that beta. Okay, and what that does is it just cleans up the equation, and what we end up with is this quantity alpha minus beta times t1 plus t2 is equal to negative h delta x squared t infinity minus gamma. Okay, so then our final equation, or sorry, our final matrix system, if we rewrite it, looks very similar to before, but the first row is different. We have alpha minus beta as the first entry, and then 1 and 0 and so on. And then the second row is 1 alpha, oops, let's make sure that this is lined up here so it makes sense. 1 alpha 1, 1 alpha, and this continues down the diagonal. Okay, and then this sort of last corner here is like a 1 in alpha in the last entry. Of course, you have t1 all the way down to t n minus 1. So we're still only solving for the internal points. And then the first entry of the right-hand side vector b is h delta x squared t infinity minus gamma. Okay, And then the second entry is going to be the same as before, minus h delta x squared t infinity. And that continues all the way down to the last entry, which, as I said before, is the same as the previous case because the right-hand side boundary did not change. Okay? And an important thing that happened here is that we maintained the tridiagonal structure, okay? And that's why you'll often see the extra two equations that you're getting from the boundary conditions, even if it's a complicated boundary condition like a Robin boundary condition, you're going to see those incorporated into those first and last interior equations, so that you can maintain a matrix structure that's advantageous. So the important point here is that we maintained our tridiagonal structure. Tridiagonal structure. And that's important, like I said before, because that structure of matrix leads to a very efficient matrix solve. We have nice algorithms for that. Okay, so let's go over a couple of notes about this direct method. So remember, for the boundary condition equations that we discretize, you have to approximate the gradient at the boundary that uses an appropriate formula. So like, for example, if you must approximate the gradient, or the derivative, the gradient at the right boundary, or right-hand boundary, let's say, you need to use a finite difference formula that looks backwards. So, for example, something like backward difference. You need a formula like backward difference. And we went over this in our homework. You saw that you're not able to use central difference at the boundaries, and you have to use an appropriate differencing scheme. Okay. In this problem, okay, we actually are using a first order method, being forward Euler, at the boundaries, while we used a second order method in the interior points, which is central difference, and that choice did reduce the global order of accuracy, or increase the global error of our system. Okay, so by using first order method at boundary, we reduced our order of accuracy, our global order of accuracy. Okay? And so we can, if we want to, we can create or use a forward or backward difference schemes that are of higher order of accuracy. And I'll give you a couple of examples. So you can use higher order schemes at the boundary if desired. So a couple of examples of that, say if we wanted to do the left boundary, dt dx equals evaluated at x equals 0. This is equal to minus 3t0 plus 4t1 minus t2 divided by 2 delta x. Okay, this is a second order approximation, and then the right boundary version of this, like the backward difference version of this, is symmetric. So tn minus 2 minus 4 tn minus 1 plus 3 tn divided by 2 delta x. That's also second order accurate. And then these two actually also preserve the tridiagonal structure. Tridiag. Diag structure. Okay, and then you can derive these using Taylor tables, like we did in a couple weeks ago. So these using Taylor tables. Okay, so let's say you're not actually thrilled with a second order accurate method. You want third order or fourth order. You can come up with a forward or backward looking scheme that is suitable for use at the boundaries. Okay, and you can use those if you need to. If you have a mixed a Robin or a Neumann boundary condition at either side of the solution there. Okay, so let's transition. I'm going to show you now a Jupyter Notebook. Okay, so I'll stop the recording on my iPad, and we'll go ahead and take a look at a Jupyter Notebook where we solve the original equation that we discussed, where we took where we use the Dirichlet boundary conditions, and then we'll also take a look at the zero flux or the insulated boundary at x equals 0 case and how you implement that. Okay, so let's see if I can get this screen recording started here. I want to be sure that I'm not failing to record this. Okay, because that would be a shame. Okay, so I think I got this working now. Okay, so let's look here. So let's go ahead and run this first cell since it's just some imports. Okay, and then let's do this. So same problem that we've been discussing this whole time. We're going to use just 10 interior points, and we'll discuss a little bit about why it's okay to use so few points. And what is meant by stability in the context of boundary value problems as opposed to initial value problems. So we're just going to set the length equal to 10, and then input our h, define our step size and whatnot. And then we, of course, initialize our solution vectors and our domain x. Now for our boundary conditions, these ones are really simple to implement. You just set the first element value to 40 degrees Celsius, and then the last element, which we'll index with -1, using our clean indexing rule, is 200. Okay, so that we already have our boundary conditions in there. Now we need to set up the matrix, the system matrix, and the way we'll do that is we'll initialize it as a matrix of zeros, and then we'll go in through with a loop and populate it with the correct values. But the way we've defined nx here, the number of interior points is just nx minus 2. Okay, so I don't actually need those parentheses there. I need it like this, and it needs to be nx minus 2. Okay, so you feed that tuple, get nx minus 2 by nx minus 2 vector, and then of course the right hand side vector b is going to be the same length. Okay, and now let's go ahead and fill the matrix. We'll use that alpha value that we defined. It was -2 minus h times dx squared. Okay, that was our value for alpha. And then now we're going to move along the diagonal we're going to move basically along the diagonal of the matrix, and we're going to set the diagonal value and the values flanking it to the values that we need for the system matrix to be of the correct form, that tridiagonal form. So the diagonal value was alpha. Okay, and then the value to the left, or I minus 1, okay, is just 1. And then the value on the right is I plus 1, I equal to 1. Okay, so nothing crazy there. And then we didn't loop, we skipped the first row here because it's different, of course. And so the first diagonal term got skipped in the matrix in that loop. And so we're left with the following. Let me see. I actually did an indexing mistake here. We need this to be I minus 1 here. And so this one is the right of the diagonal, and this is the left of the diagonal. Let's see. Does that make sense? We have I minus 1, the first index going down. See. It's actually the way that this loop is written is it's specifying the ones that are below alpha and to the right of alpha, and so it's probably just a way of only skipping the first one. There's many different ways to skin the cat here. Just write the loop in the way that makes the most sense to you to create the system matrix in the correct form. This is just how this code is adapted from Dr. Opti's textbook, so I didn't necessarily make the choice here. And so anyways, we proceed. We set our right hand side vector elements, okay, to be the value that they should be, and then we alter the first and last entry accordingly. Since we know what the boundary values are. So this is just that the first and last equation being containing the known values of the boundary values. Okay, so the last is just going to be b indexed at minus 1 minus t indexed at minus 1. Okay? And so now we'll call that numpy.linalg.solve function using a and b, and that the result of that is going to be the vector of t values at the interior points, and then we can slice our vector at the interior points, so from 1 to minus 1, and set that equal to t interior. So we're assigning the interior points to our overall solution vector. Okay, and let's see, I don't think there's anything else to fill in here, so we just go ahead. This is just an exact solution that you guys know how to find that. So if we run this, let's see, inconsistent use of tabs and spaces of indentation. Let's go up here. It looks like we have an issue here. It's just okay, let's see if this works. Yeah, there we go. Uh-oh. We've got a mismatch between our direct method and our exact method here. That's probably some sort of initialization error. Let me make sure. I can stare at the code here and make sure that I'm not making a mistake. This is fine though. This is good. It's good. It's good to make mistakes sometimes, so that I can debug in real time. You can see how this works here. So I think the code, as far as I can see, should be correct. Let me just go ahead and let's clear all the variables. It might just be because I had been running code in this notebook beforehand, so it might just be an issue with multiple definitions. No, it does not seem to be the case. Let's see. Am I performing the solve incorrectly? 1 to t minus 1 t interior. That's right. That's all right. Xt. T 200 and 40. That's all right. Let's see. T infinity is the same as before. And the I in range from 1 to nx minus 2, that's correct. Oh, see, of course. I forgot to actually finish this this line here where we set that first diagonal term. So you can see just that simple error caused a mistake there. So let's here I'll make another panel here so you can see the solution a little bit easier. So note that we actually got really close to the exact solution with only 10 interior points here. I mean, granted, the exact solution is not varying very quickly. If there was a lot of sort of rapid oscillations in space, you would have to include it. You would have to have a more finer grid, but we still get really nice performance here with just 10 points. Okay, and so let's actually go ahead and look at the Dirichlet boundary condition, just show how it differs. It's actually very, very similar. So everything is basically the same up to this line, and then in fact the similarities continue where the right-hand boundary condition is the same as before. So we're still just setting the temperature equal to a constant value at the right-hand side. But when we fill in the matrix, all the interior points are the same, but the first entry of the matrix picks up that alpha minus beta value, right? And in this case, the beta value is just -1, because like we showed in the notes just a moment ago, this boundary condition, the zero flux boundary condition, when you use forward difference, just makes the array values at the boundary be equal to the first interior point. And so what that translates to for the matrix is that AD00 is equal to alpha plus 1. And you can check this on your own if you like. Okay, and then we proceed in the same way for B. We only have to modify the last element of B this time. We don't have to modify the first because of the way the boundary condition works out. And then we have the interior, and then once we assign the interior, we have to fix the first boundary value at 0. That has to be equal to whatever TD is for T Dirichlet. Add 1. Okay, that's the left-hand side boundary condition equation that we ended up with, that we subbed in. Okay, and that's all that goes into that one. And when we run that, you can see that we get a different solution. And interestingly enough, you can also very clearly see that the temperature gradient is going to 0 at the left boundary as we required. Okay, so it's a reasonable solution. And so yeah, so it's not overly complicated. Most of the meat of implementing this is going to be creating this system matrix in the right way and creating the right hand side vector in the right way and doing all the bookkeeping. You saw how I made a slight error just reproducing this for you. Yeah, we'll have some more discussion about what stability means in the context of boundary value problems as opposed to initial value problems. But in short, what it has to do with is things like sensitivity to boundary conditions. For example, if I were to perturb the boundary condition of a poorly conditioned or unstable boundary value problem with the finite difference approximation that I used, you would see rapid variation of the solution. You can also end up with system matrices that are ill-conditioned, meaning they're difficult to invert. Or in other words, the overall equation that you're trying to solve, matrix vector equation, is nearly singular. So the solution vector is very close to 0 for all entries. that can cause some issues as well. But we'll talk about those types of issues in the future. But for now, that's all we'll go over today. Next time that we meet in person, we'll go over the shooting method, where instability is actually more of an issue. And then we'll actually start to talk about partial differential equations and go down that rabbit hole, which will be a lot of fun. So, but for now, I'll wish you guys luck on the midterm on Tuesday, and I will sign off. And yeah, I look forward to seeing you guys and returning to lecturing in person. Thanks.